Let's still talk about tensor product. Let's talk about interaction with home factor. So the first result, let's talk about disjoint. Actually, it's disjoint pair, disjointness with home. Disjointness, so tensor and home. So let's first say the statement, the first part of the exercise we want to prove. For our modules M, N, and P, 0 R module isomorphism bilinear map M and P. So which means bilinear map from M product N to P by the universal property directly. This is isomorphism to the linear linear home factor from the tensor product M with N to P. So the main part is the last isomorphism we claim. This is also homomorphism to the R linear map from M to the to the home from N to P, R linear. So in some way you say, in some sense you see there are 3 candidates and you just find a way to given 2 of it and you got the information for the 3rd, right? So yeah, so in the using the categorical language, this is exactly telling you that. So tensor product and home adjoint pair, right? So let's look at the solution of this, and then we state a related second exercise if time permits. So let's say we focus on the second part. The first part, as we said, it comes directly from the definition or universal property of tensor product. Remark is that think about home as, or think about elements of it, right? Think about elements of it. Think elements of this as a family of R linear maps from N to P, indexed by M, which means you first give me index by M, and then through this R linear map I give you R linear map FM. Notice if we have a bilinear map. Then we got a family of linear maps. Because for any small m, big M, through this bilinear map we construct Fn defined to be those who map element of n to bilinear map of this n evaluate on n. This is in P, right? So in other words, this is B n. And Fm is R linear. In other words, this is indeed here. A quick reason is that B is bilinear, hence fixing any component gives a linear. This is R bilinear, this is R linear map, right? So here we're fixing first position to M, and then it become a linear map. So actually, this second remark tells you how to construct element here from here, right? Wait a minute, yes. So you start with bilinear map. So because this is totally obvious, so can, yeah, we identify this two very easily by inverse property. So we know how to construct such map, which is our BM bar, right? We've constructed such a functor. Third remark, kind of, we are constructing the inverse function. If we have a linear map, are linear, then for any small m, we have a linear function. L m by definition from n to p. And then we hence define a map, call it BL, from M, N to P. And how do you do that? Small m, give me an N, and map it to L of M, evaluate on N. And this is R bilinear. So because Lm is linear, so the linearity on the n position is obvious. And because this L is R linear, so linearity on the m position is also obvious. So this is bilinear. And then it's just left to check that. This gives you an inverse function. Start here, we constructed a BL. We'll just check these two morphisms are inverse to each other. Then second part of the exercise is a corollary. For any R modules M and their R module isomorphism so this is what we have proved. So this is the due as R module, right? This is basically what we have proved. So add one more. We reverse the position of N and M. How to do this? So actually, this comes from, you can see there is a symmetry to M and N. We're talking about bilinear maps, right? So that directly tells you the last one. So the argument is very simple, as I said. So this is isomorphic to this just by symmetry as R modules. So we're proving all those isomorphisms as R module. This is our first part of the exercise. This is isomorphic to home, home, and to R. Wait for a while. Obviously, here the P, we are taking a particular position. We are taking a particular case. So the exercise one is more general. We take whatever P. Here we take R module. P equals R. And so this is it. And this gives you the N due, right? But also by the symmetry, you can have also here N M due. And so this is the claimed one. So nothing special. So the last part, an example, a counterexample. Counterexample what? So there is a symmetry for the tensor, but we never say that. We never say that there is a symmetry for home, right? We only say there is a symmetry for the due. And it's very easy to give counterexamples. So just take as a Z module, if you map Z to Z quotient by some N, then this is isomorphic to the quotient by M. Basically, as a, let's say it's as a real morphism. I'm just asking it as a building group morphism of Z module. So it's determined by, say, major 1. And then N must be mapped to an X bar. Wow. As a Z module homomorphism, this is 0. Because this can only be mapped to 0. You have to make sure N, one bar which is 0 bar, have to map to 0. But if whatever this is, this means the N times this must be 0, but this is a domain, so this is 0. So they're not isomorphic. Okay.